Hello everyone, and thank you for joining today's webinar on the analysis of magnetic pulse welding. I am Sumit Singh, an electromagnetic expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded inside the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all the questions at the end of the presentation. So let's jump right into the presentation. Here is the agenda for today's webinar. We'll begin with an overview of magnetic pulse welding. We'll go through its different sectors where it finds crucial application. Then we will delve into the various industries where magnetic pulse welding is making a significant impact. We'll also try to explore the critical factors that influences the magnetic pulse welding along with its fundamental principle of working, and will focus more on electromagnetic forces and their role. Later we'll introduce you with EMS for SolidWorks and will demonstrate you for how it can be effectively utilized in the analysis of magnetic pulse welding. Later I will summarize the key takeaways from today's discussion, and lastly we'll open the floor for any questions or discussions you may have. Magnetic pulse welding, which is an extraordinary high-speed solid-state joining process, utilizes to fuse two or more metallic workpieces. Its uniqueness lies in its ability to create high-quality solid-state welds at a rapid pace without excessive heat. This makes it an ideal choice for joining dissimilar materials. The overall process operates on the principle of electromagnetism and thermal effects to seamlessly join materials through the rapid discharge of high capacitance electric pulse through a coil. And then a strong magnetic field is generated, which propels the welding process forward. Moving ahead, here we have a visual representation which showcases the sheet welding and the tube welding process using magnetic pulse welding. So let's move forward and try to understand where magnetic field pulse welding finds its extensive application. So magnetic pulse welding finds its application in a multitude of industries, including automotive, aerospace, and electronics. It shines when joining dissimilar materials, such as it could be aluminum to steel or copper to aluminum. The advantage of magnetic pulse welding are numerous, including high joining speed, minimal heat affected zones, and the ability to weld materials with significantly different melting points. This process is particularly suitable for applications where preserving material properties and reducing thermal distortions are the most critical factor. In the automotive industry, magnetic pulse welding is really a game changer, allowing the welding of different materials like aluminum and steel. It's widely used in components such as heat exchangers, exhaust systems, or it could be the suspension parts. The oil and gas industry also leverages this technique for joining pipes and tubes made of different metals, and also it offers resistance to corrosion. Furthermore, aerospace industry utilizes magnetic pulse welding for joining lightweight materials like aluminum and titanium, and which aid in reducing aircraft weight and improving fuel efficiency. Indeed, magnetic pulse welding impact is far-reaching. In the electronics and electrical industry, magnetic pulse welding plays a crucial role in joining like conductors like copper and aluminum, and ensuring efficient electrical conductivity, and also, as we saw in the previous application, reducing the risk of corrosion. Moreover, in the medical devices and biotechnology sector, magnetic pulse welding is employed to create seals in medical devices, which is called as a hermetic seals, which ensure airtight and leak-proof connections, crucial for components in devices like pacemakers and sensors. So now let's dive into the intriguing working principle of magnetic pulse welding. So the process harnesses electromagnetic principles by rapidly discharging a high capacitance electrical pulse through a coil. This pulse generates a robust magnetic field around the coil and setting the stage for the welding process. The interaction of these magnetic field with a conductive workpiece induces circulating electrical currents, which is nothing but called as eddy currents within the material. And then the interaction between the induced magnetic field and the eddy currents culminates in a force known as the Lorentz force. This force acts perpendicular to the current direction and the magnetic field direction. In magnetic pulse welding, the Lorentz force plays a pivotal role in driving the welding process. So that this Lorentz force generates a magnetic pressure that propels the workpiece upward and causes a powerful collision at the interface of the workpieces. And finally, this collision leads to a plastic deformation and localized heating, and then formation of a solid state weld joint occurs. But also there are various factors which affects the magnetic pulse welding. So as we have seen, the electromagnetic forces play a critical role in joining materials. Also, the Lorentz force, which creates a concentrated magnetic pressure at the interface of the workpieces, which drive them together with high kinetic energy. So that magnetic pressure is also a very one of the key factors affecting. Then we have the plastic deformation, which is nothing but the intense collision at the interface results in plastic deformation of the materials, and this allows atoms to intermingle and form a solid state bond without reaching their melting points. And finally comes the speed and the precision at which the joining process is occurred. So since it's a solid state process, no molten material is involved, which minimizes the heat affected zone and preserving the material properties. So to address and to solve the case studies related to magnetic pulse welding, we have a EMS for SolidWorks and an advanced FEA tool developed by EMWorks. EMS enables comprehensive modeling and analysis of magnetic pulse welding, which provides insight into the complex physics of the process. Through electromagnetic and thermal simulation, EMS allows engineers and researchers to optimize welding parameters, predict weld quality, and explore new possibilities in material joining. The coupling of electromagnetic and thermal simulation empowers a thorough understanding of the magnetic pulse welding process, aiding in pushing the boundaries of the innovative welding technique. So let's proceed and see how EMS can effectively utilize in this analysis of magnetic pulse welding. So here we have a case study 1, which is a magnetic pulse welding application for aluminum and the steel sheet, and here we'll be using a E-shaped coil. So we'll look at this application and understand how to join aluminum and steel sheet using specifically designed one layer E-shaped flat coil. And the E-shaped coil structure, what you can see on the right hand side of the screen, is crucial in shaping and directing the magnetic forces generated during the welding process. So the unique geometry, what you can see, and we have taken from the reference paper, of the E-shaped coil influences the magnetic field distribution during the discharge. The shape and the configuration are optimized to generate a magnetic field, and this facilitates a strong and a precise welding process. So for the specific case study that we are discussing, the case study 1, focusing on magnetic pulse welding of aluminum and steel sheet, several initial parameters were set to achieve successful welding. So what we have done here is the initial air gap between the flyer plate, which you can see over here, and the parent plate are the crucial for the collision and subsequent welding. So was meticulously set to 1 millimeter. Additionally, the capacitor bank was configured with a capacity of 64 microfarad, which provides the necessary energy for the welding process. And the coil, which is you can see over here, has the coil inductance was around 0.02 nanohenry, and this also plays a pivotal role in shaping the discharge and the magnetic field generation through this coil. Now, to comprehend the intricate magnetic pulse welding process, it's essential to analyze the electric discharge waveform. So as you can see here, the current waveform during the discharge, which you are taking from a reference paper, shows that 9 kilojoule discharge energy provides valuable insights into the dynamic of the electrical circuit. So the waveform showcases the surge of electrical energy through the coil that passes through, and illustrating the rapid discharge and subsequent generation of the intense magnetic field necessary for the welding. Understanding this waveform aids in optimizing the welding parameters for efficient and high quality of weld. So in this fascinating world of magnetic pulse welding, electromagnetic forces are the driving factor behind the successful fusion of materials. These forces are generated by the rapid discharge of high capacitance electrical pulse through a specialized coil, which forms a robust magnetic field. This magnetic field in turn induces a current known as the eddy current in one of the pieces of the workpiece, and typically the one position below the coil. The interaction between the magnetic field and the eddy current leads to the creation of intense magnetic pressure, and this pressure causes the two workpieces, the flyer plate and the parent plate, to collide and bond at their interface, which resulting in a solid state weld joint. So in this case, understanding the material property is vital for a comprehensive analysis. The materials involved are stainless steel, aluminum and copper. So the stainless steel serves as the parent plate, providing structural integrity and stability. Aluminum, which is acting as the flyer plate, plays a significant role in the collision and subsequent bonding due to its lightweight and its malleable property. Additionally, the coil, a fundamental component of the welding process, is crafted from copper, known for its excellent electrical conductivity, and the table 1 showcases the key properties like electrical conductivity, specific heat capacity, mass density and thermal conductivity, which is essential in determining the behavior and the performance of these material during the welding process. So in any welding process, understanding and controlling thermal input are critical aspects. So for this case study, what we have done is we precisely used the thermal convection inputs for the ambient air body were defined. The initial temperature of the simulations was set at 300 Kelvin, which representing a typical ambient conditions. Additionally, the convection coefficient, representing the rate of heat transfer between the workpieces and the surrounding air, was set to 20 watt per meter square Kelvin. These parameters play a crucial role in ensuring that the welding process is conducted under realistic thermal conditions, enabling accurate simulation and analysis. So I'll just play the animation. So in this case study, we utilized EMS simulation to visualize the current density distribution inside the aluminum sheet and the coil during the magnetic pulse welding process. So as you can see in the animation, it helps us to understanding how the current flows through the materials during the welding process is occurred. The current density distribution provides a glimpse into how the electrical energy is distributed within the aluminum sheet and the coil. This distribution influences the magnetic field generation and subsequently the forces responsible for the welding process. And you can see here the varying in intensity, which is on the right hand side, of current within different region of the aluminum sheet. You can see over here. And the coil, the high current areas are indicative of significant magnetic field generation, which is influencing the welding dynamics. Continuing our exploration of case study 1, we employed EMS simulation to showcase the temperature distribution inside the aluminum sheet during the welding process. So the temperature distribution within the material is another crucial aspect of magnetic pulse welding. It influences the material's behavior, including plastic deformation and eventual bonding. This animation visually represents how temperature is distributed within the aluminum sheet during the welding process and provides an insight into the thermal effect and the heating patterns involved during the welding process. And also this temperature distribution allows us to analyze the heat affected zones and ensure that the welding process maintains the integrity and the properties of the materials which are involved during the process. Now let's move forward and delve into the second case study, which is a 1-ton coil with a fill shaper to produce the welded sample. So here we utilized a 1-ton coil, as you can see here, and with a fill shaper as shown in the brown color to produce the welded sample. This configuration involves a 3D model and a schematic illustration of the magnetic pulse welding test case. So the design incorporates a 1-ton coil, optimizing the welding process. The fill shaper, a specifically designed component, plays a crucial role in shaping and directing the magnetic flux generated during the welding process, and it also ensures a focused and efficient application of the magnetic forces required for welding. Moving ahead, understanding the input current waveform in the study case 2, where 1-ton coil and a fill shaper are utilized for welding. So if we take a look at the waveform, the input current waveform is the driving force behind the generation of the magnetic field within the coil and the fill shaper. So you can see a surge pulse of current has been supplied to the coil. This waveform is typically a high energy pulse, initiates the welding process by creating a strong and focused magnetic field, leading to the desired collision and then subsequently bonding between the materials. Analyzing this waveform provides an insights into the energy dynamics of the welding process, assisting in optimizing the process for efficient and precise weld. You can go and create multiple parameterization scenarios, and we can have several case studies to run and optimize the complete welding process. This waveform is taken from one of the prototype from one of the reference paper. Moving ahead, again, material properties is an important factor. So the material involved include here is aluminum alloy, which is for the tube and rod part. Copper alloy is for the fill shaper, and the steel for the coil. So material properties such as density, electrical conductivity, specific heat capacity, and thermal conductivity are essential in determining how each material behaves during the welding process. So understanding this property aids in accurately simulating the electromagnetic and thermal dynamics and is crucial for achieving the successful weld. And the table showcases the specific value of this property of each material that we involved during the simulation. So let's explore the thermal input of this case study. So in this case study, we were focused on welding using a 1-ton coil and as well as the fill shaper. So the thermal convection input for the ambient at body was around 298 Kelvin. This was the initial temperature set for the simulation, and the convection coefficient is set to 10 watt per meter square Kelvin. And it's again understanding and thermal environment is essential for the accurate simulation. So to ensure that the thermal effects are accurately taken into account, we need to have a parameterization analysis and see the influence of the behavior of the materials during the welding process at different initial temperatures or at different convection coefficient. So for the case study 2, we again utilized EMS simulation to visualize I'll play the animation. Okay, the magnetic flux density distribution after a half period of the first pulse of the input current. And understanding this distribution of magnetic flux density within the material is very important. It will help us to directly correlate to the magnetic forces that will drive the welding process. By visualizing this distribution, we gain valuable insights into how the magnetic field is concentrated and specifically in the region crucial for achieving the weld. And as shown in this animation over here, the magnetic flux density is distributed across the materials that is involved. You can see over here, areas of intense magnetic flux density are particularly significant and indicating strong magnetic forces that add in a material collision and the bonding. Moving ahead. So in this segment, we compare the magnetic flux along the mid-plane of the fill shaper at the outside surface of the tube using both reference data and the EMS simulation result. So as you can see, the black waveform represents the EMS results and the red one represents the results that we obtained. We took it from the one of the reference paper listed at the end of the presentation. So this comparison allows us to validate the accuracy of EMS simulation results by aligning them with reference data. This graph showcases how well EMS simulation align with established data and ensuring that our simulation accurately represents a real-world phenomena. Analyzing and comparing this magnetic flux profiles is instrumental in fine-tuning the simulation parameters for precise and reliable results. So continuing with the case study 2, let's visualize the temperature distribution inside the tube, a crucial aspect of understanding the welding process again. So temperature distribution within the tube is fundamental as it directly influences material behavior and the welding outcome. The animation, what you can see over here, provides a dynamic view of how temperature evolves within the tube during the welding process, highlighting these areas of high temperature and potential material transformation. So again, it's very important to understand the temperature distribution and what's a peak value that a material can handle, which helps in optimizing the welding parameters, ensuring the desired weld quality and the material properties are achieved. So now let's explore how to simulate the model we have discussed so far during the presentation and using an EMS software, and here are the steps to achieve this. So as we can see here, AIMWorks products are adding to a SolidWorks. So to simply activate the product, you need to go to add-ins, and here you'll be able to see the AIMWorks product which can be activated using this checkbox option. Once these products are activated, you need to simply go to tools and click on the AIMWorks product, and here you will be finding an EMS which can be launched. You can start the demo viewer to try with our new software. So once your design is ready, so let's say this is a design for a magnetic pulse welding. So once the design is ready, it's time to create a study. So for that, we'll simply click on the EMS. If it's a 3D geometry, we use EMWorks 2D Manager. If it's a 2D geometry or 2D application, So since it's a 3D geometry, I'll be clicking on EMS Manager, and here I'll have the study property, which can be created by clicking on the right, using the right button. You can click on select the study feature, and from here you can choose the different types of analysis, whether it's a magnetostatic, AC magnetic, or transient magnetic, or for the electric field analysis such as electrostatic, electric conduction, or AC electric. You can use the coupling analysis to couple your model with thermal, structural, or motion. And here we have some advanced settings for meshing. It could be adaptive or manual, and some advanced property. So once the study is created, the next step is to define the parameters and setting up for your simulation. This includes specifying the material properties, which play again a crucial role in accurately modeling electromagnetic behavior. And so you have to simply go here, expand the material section, and assign materials to different components of your model. Whether for a coil we are assigning a copper material, for stainless steel for the parent plate we have assigned a stainless steel, and for the flyer plate we have assigned an aluminum body. This library is easily accessible on the right side of the window. Here you can find all the material which are commonly used, and of course it's customizable, so you can always add a new material as per your requirement. Next comes define the boundary conditions. So here we have conditions for electromagnetic input and the thermal input. These conditions specify how your design interacts with external environment. And then to solve complex electromagnetic problems, your design needs to be divided into smaller elements, which is called the mesh. So that's the next step. Here you can create the mesh and use a mesh control feature to have a more coarser mesh or more finer mesh for a particular section, whichever you feel like. I can simply show you the mesh generated for the model what we have today. So this is a mesh for the components. Now once everything is done, you can assign the desired current and voltage. You simply go to coils, you assign a current and either voltage source within your design. So once all the steps are complete, it's time to solve the simulation. EMWorks uses advanced numerical solvers to calculate electromagnetic field distribution, losses, and other relevant parameters based on your design inputs and parameters. So I'll go through the results section. Here we have results for electromagnetic and results for the thermal input that we have. So EMWorks offers advanced post-processing capability, and we do have a contour plot. I can simply create a new fringe plot for this. So here is the fringe plot, and you can also even change the fringe plot to vector plot, section clipping, and you can use for a data extraction tool. In addition to this static plot, EMWorks also provide animation capabilities. So you can simply right click on the plot and use this animate option. So you can create a dynamic visualization by animating the changes in electromagnetic field quantities over time. This features enables you to observe transient phenomena and such as the propagation of electromagnetic waves or the response of a design with varying inputs. So I'll just zoom it over here. Moving ahead. So these were the results which helps you to visualize and understand the magnetic welding pulse process, and also how do we use EMWorks software to analyze and to solve such type of models and assign the materials, coils, meshing it, and post-processing these data. Moving ahead, so in conclusion, today's webinar has delved into the remarkable capabilities of finite element analysis through EMS software. We have explored the intricacy of magnetic pulse welding, a process that harnesses the principle of electromagnetism and thermal effects to join materials efficiently and with precision. By minimizing heat affected zones and preserving material properties, magnetic pulse welding is a game changer across various industries. The simulations and analysis we have discussed today demonstrate the power of FEA in understanding, optimizing, and innovating welding processes. The case studies illustrated how EMS simulations provide crucial into current density, temperature distribution, magnetic flux density, and more, shaping the understanding and advancement of magnetic pulse welding. So, here are the references for today's webinar, and we appreciate the invaluable insights and research that have contributed to today's discussion. We would like to extend our heartfelt gratitude to each one of you for joining us today, and your presence and engagement have made this webinar a success. If you have any further question or need any additional information, please type your question using the chat box option. Thank you once again and have a wonderful day.